Collagen extraction from jellyfish, characterization, sustainable valorization, and emerging applications in the circular bioeconomy. Collagen is the most abundant structural protein in animals and a critical component of the extracellular matrix, ECM, providing mechanical strength, elasticity, and structural organization to tissues. Traditionally, commercial collagen has been derived from bovine and porcine sources for applications in cosmetics, nutraceuticals, tissue engineering, wound healing, and drug delivery. However, growing environmental concerns, zoonotic disease risks, religious and ethical restrictions, and the substantial carbon footprint of livestock production have accelerated the search for sustainable, safer alternatives. In this context, marine-derived collagen, particularly collagen extracted from jellyfish biomass, has emerged as a promising bioresource for blue biotechnology and circular bioeconomy initiatives. Jellyfish are increasingly abundant in many marine ecosystems, especially in the Mediterranean Sea, where warming ocean temperatures and eutrophication contribute to frequent blooms. Although jellyfish are natural components of marine food webs, their accidental capture as fisheries bycatch creates operational and economic burdens for small-scale fisheries through net clogging, gear damage, increased fuel consumption, and reduced catch quality. Recent studies have demonstrated that this underutilized biomass can be transformed into a valuable source of high-quality collagen, thereby converting marine waste into a commercially relevant biomaterial within a circular economy framework. Among Mediterranean species, the barrel jellyfish, Rhizostoma pulmo, has attracted significant attention due to its high collagen content and favorable biochemical properties. Jellyfish collagen primarily consists of collagen types 1 and 2, although structural analyses suggest that it differs substantially from vertebrate collagen and may represent a distinct collagen subtype sometimes referred to as type 0. Similar to mammalian collagen, jellyfish collagen possesses the characteristic GlyXY repeating amino acid sequence, where glycine, proline, and hydroxyproline stabilize the triple helical structure. However, jellyfish collagen generally contains lower hydroxyproline content, resulting in reduced thermal stability and lower denaturation temperatures compared with mammalian collagen. The extracellular matrix of jellyfish, known as the mesoglea, is exceptionally rich in collagen and provides structural integrity, buoyancy regulation, locomotion support, and regenerative capacity. Importantly, jellyfish-derived collagen demonstrates excellent biocompatibility, low immunogenicity, and minimal risk of transmitting mammalian pathogens such as bovine spongiform, encephalopathy, or viral contaminants. Human cells readily recognize jellyfish collagen, supporting cell adhesion, proliferation, and tissue regeneration, making it particularly attractive for biomedical applications. Recent interdisciplinary research involving marine scientists and Mediterranean fishing communities has demonstrated the feasibility of utilizing jellyfish bycatch as a sustainable collagen source. Monitoring programs conducted between 2024 and 2025 identified Rhizostoma pulmo and Pelagia noctiluca as the dominant bycatch species in small-scale Mediterranean fisheries. Importantly, collagen extracted from accidentally captured jellyfish retained structural integrity comparable to collagen obtained from carefully hand-collected specimens, indicating that bycatch collection does not significantly compromise collagen quality. Extraction of jellyfish collagen. The extraction of jellyfish collagen typically begins with extensive washing and cleaning to remove salts, debris, mucus, and contaminants. Depending on the protocol, either the entire organism or selected anatomical regions, such as the umbrella and oral arms, may be processed. Because jellyfish contain approximately 95 to 97% water, Pre-treatment methods such as homogenization, freeze-drying, or tissue fragmentation are commonly employed to improve solvent penetration and extraction efficiency. A standard extraction protocol for acid-soluble collagen involves alkaline pretreatment using 0.1 molar sodium hydroxide to remove non-collagenous proteins and pigments without significantly altering collagen structure. Lyophilized jellyfish tissue is suspended in NaOH solution, typically at a 1:50 weight-to-volume ratio, and stirred continuously for approximately 24 hours at 4 degrees Celsius. Following repeated washing to neutral pH, the pretreated tissue is subjected to acid extraction using 0.5 molar acetic acid under constant agitation for up to 72 hours. Acidic conditions promote collagen solubilization by disrupting intermolecular interactions and increasing electrostatic repulsion between collagen fibrils. After extraction, insoluble materials are removed by centrifugation, and collagen is precipitated by salting out with sodium chloride. The precipitated collagen is subsequently redissolved in acetic acid and purified by sequential dialysis against decreasing concentrations of acetic acid to remove salts, residual acids, and low molecular weight impurities. Finally, the purified collagen is freeze-dried to obtain a stable powdered product suitable for downstream applications. Alternative extraction technologies have also been investigated to improve yield and sustainability. Pepsin-assisted extraction selectively cleaves telepeptide regions and enhances collagen solubility, while preserving the triple helical domain. Ultrasound-assisted extraction improves tissue disruption, solvent penetration, and mass transfer, substantially increasing extraction efficiency and reducing processing time. Emerging green extraction strategies, including supercritical carbon dioxide extraction and deep eutectic solvent systems, are being explored to minimize environmental impact and reduce chemical consumption, although their application to jellyfish collagen remains at an early stage. Characterization of collagen. Structural characterization is essential to confirm collagen purity, molecular integrity, and preservation of the native triple helical conformation. Sodium dodecyl sulfate polyacrylamide gel electrophoresis, SDS-PAGE, is commonly used to evaluate molecular weight distribution and protein composition. Collagen extracted from Rhizostoma pulmo exhibited characteristic alpha-1 and alpha-2 chains with molecular weights of approximately 150 and 160 kilodaltons, respectively, along with beta-dimer bands near 260 kilodaltons. The electrophoretic profiles of collagen derived from hand-netted and bycatch jellyfish were nearly identical, confirming that fisheries bycatch did not induce significant molecular degradation. Fourier transform infrared spectroscopy, FTIR, further verified the preservation of collagen's molecular structure. Characteristic amide absorption bands associated with collagen were observed, including a mid-A around 3,278 per centimeter, a mid-B near 2,918 per centimeter, a mid-I at approximately 1,644 per centimeter, a mid-2 near 1,551 per centimeter, and a mid-3 around 1,234 per centimeter. These bands correspond to NH stretching, CH2 asymmetrical stretching, carbonyl vibrations, and peptide bond interactions characteristic of native collagen fibrils. Similar FTIR spectra for hand-collected and bycatch-derived collagen confirmed structural consistency between extraction sources. X-ray diffraction, XRD, analysis provided additional confirmation of collagen's native fibrillar architecture. Distinct diffraction peaks at approximately 2 theta equals 8.6 degrees and 19.4 degrees corresponded to intermolecular spacings characteristic of intact triple helical collagen structures. Calculated interplanar spacings of approximately 10.27 angstroms and 4.57 angstroms further indicated preservation of the native molecular arrangement. Collectively, SDS-PAGE, FTIR, and XRD analyses demonstrated that collagen isolated from jellyfish bycatch retained its structural and biochemical integrity. Applications of jellyfish collagen. The extracted collagen exhibits considerable potential across multiple industrial sectors. In nutraceuticals, hydrolyzed jellyfish collagen peptides possess antioxidant and anti-inflammatory properties and are increasingly explored for skin, bone, and joint health supplements. In cosmetics, jellyfish collagen functions as a moisturizing and bioactive ingredient with potential applications in anti-aging formulations and UV protective products. Biomedical applications are particularly promising, including tissue engineering scaffolds, wound dressings, cartilage regeneration matrices, hydrogels, and drug delivery systems. Studies have shown that jellyfish collagen scaffolds support mesenchymal stem cell differentiation, vascularization, chondrogenesis, and reduced immune responses relative to mammalian collagen materials. From a sustainability perspective, the valorization of jellyfish bycatch aligns strongly with circular bioeconomy principles by transforming problematic marine biomass into high-value bioproducts. This approach not only reduces marine waste, but also creates additional income streams for coastal fishing communities, while enhancing fisheries' resilience under changing environmental conditions. Collaborative initiatives integrating scientists, fishers, and blue biotechnology industries demonstrate how local ecological knowledge and sustainable resource management can support innovative marine biorefineries. Challenges and future perspective. Despite its promise, several challenges remain. Jellyfish are highly perishable and logistically difficult to process because of their high water content. Potential contamination by marine pollutants, including heavy metals and microplastics, requires careful monitoring and purification. Furthermore, the natural variability of jellyfish collagen composition and the need for scalable industrial processing infrastructure remain significant barriers to commercialization. Nevertheless, current research strongly supports jellyfish-derived collagen as a sustainable and biocompatible alternative to mammalian collagen. By integrating fisheries management, marine biotechnology, and circular economy strategies, jellyfish biomass may become an important renewable feedstock for future biomedical, cosmetic, and nutraceutical industries, while simultaneously addressing ecological and economic challenges associated with jellyfish blooms and fisheries bycatch.